Okay, so hello everybody, and thanks very much for inviting me to present today. A lot of our team's work focuses on the challenges of coordinating observing programs, particularly for time domain science. And I'd like to tell you about two of the software tools that we've developed for that purpose. But before I go on, I want to give all credit to the TOM team, especially our lead developers, David Collom and Lindy Lindstrom. Both of these projects have developed from a really productive collaboration between the software engineers and the astronomy team at LCO. So to give context for these projects, I want to quickly recap the scientific motivation. Everyone here will be familiar with some of the challenges we face in deriving science from modern surveys. Alerts of new discoveries per night are expected to increase by an order of magnitude over the next few years. And the survey data products in total are reaching the petabyte range. As you know, many astronomers are highly motivated to react to new discoveries in real time. So we're all faced with this challenge of sorting out our preferred type of wheat from the chaff. We need to select targets of interest to our science and collate all available data. Other speakers in this forum have describe the broker facilities which are designed to address this problem. But once they've done their job, I'm interested in what's the next step. So I, as an astronomer, have selected my candidates from the alert stream. I'm going to want to combine information from many different sources, and I'm going to want to easily review that information for my particular targets. But for most science, the discovery data alone isn't enough. So I'm going to need to obtain follow-up observations as well. Even though any one astronomer or team may only use a fraction of the original alert stream, they still have a lot to keep track of. There's this constant stream of alerts coming in with new discoveries to be evaluated, often within hours. Some of the targets will need further observations, and you have to identify which targets those are, prioritize them, and decide on what an appropriate observing strategy is. That means you're constantly juggling lots of different targets and different phases of evolution, some new and some the target of long-term studies. Quite often, teams have to manage observations involving a number of different telescopes and instruments in order to characterize a single target. And although the data products involved are smaller than those for a survey, there's still an awful lot to keep track of, more than is really feasible for even a team of humans. Just the follow-up data alone can involve thousands of observations and even terabytes of data. And not least, you need to coordinate the human team behind your project. These days, they're often geographically distributed, and everybody needs to be able to have easy and timely access to the project's data. So faced with this information overload, it's clear that astronomy would benefit tremendously by taking advantage of some of the database tools that have been developed to manage the projects themselves and all the associated data products. As a general category of software, I'm going to refer to these as target and observation managers, or TOM systems. A number of teams have independently developed TOM systems for a wide range of projects, for a wide range of different science. Dmitry Duev, for example, gave a recent example of the very impressive BRITS system presented to this forum, and that incorporates the functions of both the broker and those of a TOM. Some other examples that you may be familiar with include the supernova exchange, which is essential to coordinating the observing program of the Global Supernova Project. Although TOM systems are particularly powerful for transient science, I did want to point out that they're by no means restricted to that field. And TOM systems are currently in use for both stellar and exoplanetary astronomy, as well as for solar system studies. I've given screenshots here of some of the LCO-based projects that are run using TOM systems, simply because I have access to them, but there are many other examples that have been developed elsewhere. Although TOM systems run some major science programs, most of the original systems were developed independently. When I compared some of them, it was interesting to find that there were substantial areas of overlapping functionality, even from TOMs from quite different science areas. Although obviously there are also some areas where each of the programs had quite distinct requirements. But one thing I did find was common to all TOM systems is that the developers had to invest substantial effort to learn about the databases, to invest in software development and in the IT, and that they felt that took a lot of time away from the astrophysical research that most astronomers are actually paid for. Even if the source code for an existing TOM system is publicly available, adapting it for another project is actually a substantial effort. Developing these first generation TOM systems required the investment of a lot of energy and effort and time, but also expertise that is not necessarily available at every institution. And as these tools are such a powerful way to enhance an observing program, this becomes an equity issue. So the goal of the TOM Toolkit was to provide an easy-to-use package that enables any astronomer to build and customize a TOM system for their particular science. Our approach is to have the core package developed and supported by LCO's in-house professional software engineers, working in close collaboration with astronomers both at LCO and also in the general community. Our goal here is to maintain high coding standards and follow best practices so that the package is maintainable and developed over the long term, but at the same time respond to users' needs. So we aim to provide a base toolkit that supports the commonly used functions and interfaces, and so that we avoid each user having to reinvent the wheel. And we also designed it such that even a novice developer would be able to customize it to their own workflow. Before I demonstrate the toolkit, I'd like to give a quick overview of some of its main features. At the heart of the TOM, of course, is the central database, and we have designed it to support the astronomical targets and data products. Although a lot of the targets have some common parameters, such as RA and DEC, for example, each project is also going to have some specific parameters that are unique to its science base. And for this reason, we designed the database to allow the user to include these quite flexibly. The toolkit provides a number of built-in interfaces to most of the commonly used services in astronomy, so that the users don't have to repeatedly invent the wheel. This includes several of the alert brokers and data catalog servers such as SCiMMA, so that users can collate data from multiple sources. And of course, accessing observing facilities is a very important aspect of many TOM systems. So the toolkit includes interfaces to a number of programmably accessible telescopes, as well as observation planning tools, such as a target visibility calculator. And I want to emphasize that we actively seek partnerships with other service providers in astronomy to make sure that we support interfaces for as many of these common user facilities as possible. And I'd like to thank many of the people who have collaborated with us already, giving interfaces to brokers such as Antares, Laser, Alerce, and telescope operators such as the Liverpool Telescope and the Gemini observatories. So when it came to the user interface for all this, it made sense to focus on a browser-based display, as this can be accessible without requiring users to install a separate client software, and it's accessible by team members around the world once TOM is deployed to a public server. We chose to use the Django framework to provide this because it gives a Python wrapper, which makes it accessible to most astronomers, and it gives access to a number of different databases, so users can choose whichever they prefer with the minimum learning curve. It also provides a very flexible framework for building browser-based displays, which is designed to be extended and customized. And it also handles things like user accounts and authentication, so that's another aspect of the maintenance and IT that the users don't have to worry about. Every astronomical package, of course, or project, of course, has its own preferred ways of doing its analysis. And there's a lot of tried and tested soft packages in astronomy used for data reduction, for modeling and analysis. It's important scientifically that a TOM system be able to interface with this user-developed software, for example, to provide information on targets or to receive the results of modeling or target selection. So the toolkit provides a RESTful API to enable that sort of interaction with user-developed code. And that's an important aspect because it enables some automatic observing programs where a TOM system can be programmed to select targets from an alert stream according to some predefined criteria, conduct observations according to some strategy that's already defined, and download and analyze the resulting data. And that loop can happen entirely programmatically. It's an extremely efficient and highly reactive way of observing. So now I'd like to give you a quick walkthrough of a TOM system. When a user installs the toolkit out of via pip, it isn't just an install library. It comes with a TOM system out of the box, which we encourage users to then customize to their needs. So what I'm going to demonstrate now is the basic out-of-the-box system. Okay. And switch to browser. Okay, so hopefully you can still see this screen.
Yep, looks good.
Great, thanks. So this is the home screen, and although this is straight out of the box, I've added a few targets to it for the purposes of demonstration so that I can show you some of the key functions in actions. But I haven't customized it in any way, so you will get a feel for what you get when you install the toolkit. You can see here on the right-hand side that the latest updates of stuff that has been submitted to the TOM have been presented automatically, provided the user has access to those targets. And user permissions is something that I'll come back to shortly. So if I go to the targets page, typically the first thing that a user wants to do is load some targets into the TOM. And if I scroll to the bottom here, you can see it gives a summary table and display of the targets, as well as providing some handy search functionality on the right-hand side. By default, we include a number of interactive displays, built mostly using the Plotly package. For example, you can see here the target's spatial distribution displayed, and if I mouse over, you get more information on each one at a glance. There are a number of different ways to add targets to a TOM. You can manually enter the details by clicking on this, and you can see some of the default parameters that you're able to enter there. You can also import a catalog of targets in CSV format. So if you have a lot of targets that from an existing project to upload, you can enter them that way. And you can also do a direct catalog search from a number of commonly used catalog servers, including Simbad, NED, JPL Horizons, and so on. So, of course, for SCiMMA users are likely to get a lot of their targets from broker services. And the TOM offers built-in interfaces for a number of the existing brokers. And it allows you to describe query functions to be run on those broker services. So as by way of an example, I've set up this galactic plane query, which happens to be for targets of interest to me personally. It's recent targets within some very simple constraints of the galactic plane. And that, you will notice, is actually stored in the TOM so that you can rerun it at any time for convenience. Now, I don't know whether ZTF will have actually produced any targets or not. Oh, it did. Great. Excellent. So now you can see that I can select any targets of interest to me. I can go and view them. So if I want to find more information on these, now of course I can't get Control tab, there we go. I can go to the Mars broker directly and see more information on that target. And if I decide it's of interest to me, I can simply select it and create the target in the TOM. Now, we'll come back to this shortly because David has a more detailed demo of how we envision this workflow taking place using SCiMMA's tools. So we'll return to that shortly. Now, once a user has ingested her targets, the TOM automatically provides an overview of all of the information currently available for each target. The layout of content of all of these pages can, of course, be fully customized. And I know a number of teams have organized their pages quite differently to suit different workflows. In the basic TOM, we provide a set of tools that we think are generally useful. So the default page provides an overview for the object's essential parameters. And if I scroll down here, you can see that it also includes an interactive finder chart from SDSS. And in this first tab, you see the sequence of different data types are available through different tabs. In the first one, it presents you with a number of tools for planning observations, starting with the lunar separation available at the bottom here, and it gives you also a visibility calculator. And it also has a comments function. So this is particularly useful when a team is geographically distributed and different people are looking at the targets from different time zones. You can record comments for future reference from the team. When a target is created from an alert, the TOM also ingests the data provided. So for this ZTF example, you can see it's automatically produced an interactive plot of the ZTF photometry that it pulled from the broker. Now, if I go to the Observe tab here, you'll see the sequence of options for requesting observations for different telescope facilities. Now, of course, you have to get a time allocation allocated in advance. The TOM can't help you with that part. But I'm going to use this, the LCO option, because I have time already allocated there. And you can see that this gives you an overview of the visibility from all of the different LCO sites. And it gives you a number of different forms for requesting different types of observation. So you can request a single imaging sequence. You can do a single spectral sequence. And you can also do more complicated sequences. So for example, on this one it allows you to do multi-band imaging within a single form. So users have that for convenience. Now I wanted to show you what happens when you have observed something. So I scheduled some observations in advance of a cluster that I studied for my thesis. So I'm going to go to this target now to take a look at some of those data products. Now, if you go to the Observations tab, you will see that you have a list of the observations that I requested earlier and their status, which you can update by querying the LCO Network's API. Some of those observations have completed, so they have associated data products with them. And you can view these by taking a look at the Manage Data tab. Now, in this case, they were imaging observations, so you can inspect those directly by clicking on the Open in JS9. You also have, this gives you the option to do various functions to examine the data conveniently in the browser. And you'll notice you also have the option to upload various different other data products that might be associated with your program. The other thing I wanted to demonstrate is that security is usually an issue for any system that is going to be deployed to a public server. But of course, most astronomers are not expert on handling internet security or user accounts. and nor do they want to be, quite honestly. So the toolkit takes advantage of Django's user account tools and provides administrator interfaces so to take care a lot of these very common project management type tasks. Now, at this point, I'd like to return to the slide deck to describe a couple of features which are easier to explain this way. The first is regarding the access control permissions that I mentioned earlier. By default, any TOM user can access everything in the TOM, but we recognize that not all projects can work that way. So the toolkit allows user groups to be set up, and the administrator can nominate users to belong to one or more groups. And users can then indicate which groups should have access to which targets by selecting the appropriate checkboxes, as you can see here from this section of the target create view. Similar access controls can also be applied to records of observations and to data products at the discretion of the administrator. One of the most powerful capabilities of a TOM system is to reduce the workload of an observing program. It's often the case that astronomers can define their observing strategy in advance, even if they don't know exactly what their targets will be. For example, when a supernova is detected, an observing team who have applied for time on a given telescope know that they're going to want to get a series of time series imaging in multiple filters, probably every few days, and similarly for spectra. And they'll probably need to continue that process for a couple of months. So a common situation is that a team can nominate a suitable target and request a set of observations, but then have weather or some other factor conspire to interrupt that time series. If you have hundreds of targets to monitor at any given time, keeping track of those observations can become quite a high workload on the humans. So the toolkit supports observing strategies, which essentially enable the TOM to carry out a predefined observing strategy for you. Users can write small Python functions which tell the TOM what to do under certain circumstances. And as an example, the toolkit includes some code where it will automatically resume an expired observing request and resubmit it in the event that the initial request ended or expired without having obtained the data that you wanted. To make the toolkit really useful to astronomers, we take a very proactive approach to user support, and we've consciously designed the toolkit for all of astronomy rather than focus on just one field or one project. We have extensive documentation available online, which describes all features in detail, together with a number of how-to tutorials. You'll also find links there to a number of open source repositories for TOM systems that have been developed for a range of different science cases, as well as projects as well. We've also set up a Slack channel, which is open to everybody, and users are encouraged to use it to contact our development team directly with any questions. We also host regular virtual meetings for the community, where we share updates on new features, ask for feedback, and we also feature TOM systems that have been developed by the users. Towards the end of last year, we also hosted a public workshop in collaboration with LSTC for the community to learn more about all aspects of the follow-up ecosystem infrastructure, and also to have hands-on training to build a TOM system, working directly with our software engineers. All of the training materials and recordings of the workshop sessions can be found online at the link given there. We also arranged for attendees of this workshop to get access to a unique proposal opportunity, which offered both funding and telescope time at Gemini, SOAR, and LCO. A range of projects were selected by our TAC, from stellar astrophysics to transients to solar system science. And these projects started in December 2019. So Although they were underway, they were unfortunately impacted by the pandemic shutdown of observatories. So what we've done is we've actually extended those programs through into 2021A. So that was a quick overview of the TOM project as a whole. And before I go on to talk about our second project, I'd like to hand over to David to give a demonstration of a TOM system workflow specific to SCiMMA.
Yes, thank you, Rachel. Curtis is largely going to be narrating this because he has a better understanding of some of the science implications, but I'll be driving. I'm David Collom. I'm the lead developer on the TOM Toolkit, and Curtis, I'll just share my screen and then let you go ahead.
Sounds good. I'm Curtis McCulley, an astrodata scientist at Las Cumbres Observatory. So I work on pipelines, but I also work on other data and connections to astronomy, things like that at Las Cumbres Observatory. All right, so what we want to show today is a possible workflow you might have if you had a gravitational wave event. So you can imagine first starting with a gravitational, so LIGO and Virgo trigger something. For example, the S200114F, which was the first gravitational wave burst event that happened. And we're actually going to use that as kind of just a test case for this demo. So what you can start with is somehow you're going to get notified of this event. Maybe you hear about it on Twitter. Maybe you have your TOM alert you. So something that's we've built into the supernova exchange that Rachel showed very briefly, but it's not quite in the base TOM toolkit, is you can send text messages when you get certain alerts. So that happened for the previous ones for the supernova exchange. So you get a text message that says, okay, there's a new gravitational wave event. So now let's go learn something about it. Let's go see, is this interesting for us to follow? So the first thing we want to do is we want to find that alert and connect to that alert in the GraceDB, which is the LIGO's pages for this alert. So what David's going to show now is going through alerts. And so we're going to find the particular alert we're interested in. So we're going to actually use the SCiMMA pages that we've been developing. Now, one of the things is this is all done specifically here in the TOM toolkit. So none of this is actually calling the SCiMMA apps themselves. This is integrated directly with the toolkit. So we're going to search for this event, and we found some of the follow-up for this. And so, David, are we going to show the? Do we have the link to the GraceDB? Yes, excellent. So you click on the event, and all of a sudden it takes you to the LIGO page, and it shows you the sky visualization. So this was one of the reasons this was an interesting target, besides it being the first burst target, was that it had a very nice small sky localization. So there's some chance we might actually be able to do something and to try and find an electromagnetic counterpart. And in fact, we did try to do this at the time. No good candidates were eventually found, but this is the type of workflow that you would still go through to get there. So we've got a sky localization now. One of the things that's in process is, and we've shown a proof of concept of, is in some of these, so we can either use a broker or we can use some of the Mars DB things to say, okay, what targets are overlapping this coordinates? Like, so what patch or what target should we be following? So if we go back to our TOM now, let's say we're going to start by looking at the interesting Swift targets, and that's all in these Swift alerts here. So for this particular target, the best candidate was this X2 candidate, which is shown here. Now, with just selecting it and clicking a button, we can create a target in our TOM for this. And lo and behold, we have a new target to go look at. If we click on that, it will then give us a detail page about that specific Swift target. So this was an X-ray source that Swift detected that was in the localization region. And so this is maybe something we might want to go follow up. And so
just to clarify one thing, Curtis, this is you're taking things, Hopscotch is carrying the GCNs through Kafka, and this is a machine readable GCN that then, you know, the Hopscotch is carried, it's been read into our database, and then the TOM toolkit is looking at that database, and then you're creating a target that's creating a new entry into the TOM database, right?
Yes, that's absolutely correct.
Okay, go on.
So what this does is now not only so this has now gone from, you know, SCiMMA has mapped this target and kept it in a database kind of for the whole community, but now you have an individual copy of information about this in your local TOM. So this is for, say, an individual user. So what do I know about this object? So one thing you might want to do is, okay, I'm going to go get a spectrum of this. So if we click on the LCO tab right up there, it should give you a site. So A, it's going to show you an observability plot of when is the next time this is visible in the next few days. And it's going to give you the chance to, so if you click on spectra, we can submit a Floyd spectrum. We'll give it a name, the burst event, choose a slit. And with a few clicks, and also I will point out that this is done with just the default TOM. So we haven't included all the defaults. For many of our customized TOMs, you'll include defaults for your program. So maybe 1800 seconds. So these would autofill for most customized TOMs. But in the end, all you have to do is fill out those fields and click submit. And this has submitted a real request to the LCO observing queue, which we can see here. So with just a few clicks, we've gone from ingesting an alert that was automatically produced by Swift and put into Hopscotch and Kafka via Kafka. We've then pulled it into our TOM, and we've now submitted an observing request for that same target. So now let's go back and let's look at a few other things we can do. Okay, so say instead of, okay, that's an X-ray candidate, but you know, it's maybe not the greatest candidate. Let's go see what about ZTF targets near this region. So we're gonna go now do an alerse query on this place, or for this target. And the alerse queries take a few seconds to run. And so now we can go search for events that are close to this RA and DEC in this case. In the future, this is something we very much want to have overlapping this, you know, the whole probability region. And so that's something we've shown a proof of concept in previous meetings, but it's not fully implemented yet. So say we want to go search around this RA and DEC and around the time of this event. This is some of the Dash implementation. So in previous iterations of the TOM toolkit, this was basically a static page, but we've now, using Dash, we've started to make this a little more interactive. Alerse is a bit slow. Again, I apologize.
So what were you doing there? Just typing the date into the Dash table?
Yes, that's right. So, and then what we're going to do, so we're basically going to set the date range to within a few days of the burst event. And then we'll set an RA and DEC filter to get things that are close to the region of interest. We also only want supernovae. So we're going to limit our things to not bogus objects, for example, and or known AGN and things like that. So we're going to filter those out in a second. This does illustrate, though, how important it is to really have high performance tools. So when you compare in this particular instance, when you compare the time it takes to query alerse versus the SCiMMA tables, it's quite different. So, and then, yeah, can you add just the RA and DEC now, David? So I think this is also one of the things that SCiMMA could really help with by collating some of this data and helping to write these to write these queries to basically pull all this information into one place. It wouldn't be a live demo if there wasn't at least one issue along the way. Okay, and so now we're gonna have this target from ZTF that's close to the RA and DEC that we were interested in. This particular one is a more recent target, but either way, we can go through and we can say request a Gemini spectrum of this target because this could be an interesting ZTF target. So we're not actually going to do that at the moment, but David, if you want to click on the Gemini tab just to show what that looks like. Again, with relatively little effort, rather than using switching tools in a single place, you can then submit observations to all these different observatories. And you can see that this form looks a lot different than the one for LCO because Gemini has different constraints and things like that. And so it's both customized, but it's also in a single location to do all this. And then finally, what we can do is say we did get the spectrum that of the X-ray target that we looked at the beginning. Now we basically just mocked this, that we got an observation of this. But once we have this, we can then click a single button that submits it back into Hopscotch. So submit to SCiMMA back. And then, so it is done, it's pushed back there. And now this has sent a new alert into Hopscotch such that any other TOMs that are connected to this system will then receive an alert as well that we've gotten observations of this particular target. And so you start with a fully automated, like machine readable thing that reads in the alerts. And then, as a user, you decide which targets are interesting and you send out you make your observation requests, and then in a single interface, you can then send that information back up to SCiMMA so that you can coordinate across different things or different facilities. And if you look here, here is the actual alert we just posted. And so now this is in the Hop client. So there's a full end-to-end kind of workflow here. And so I'm happy to take any questions or any comments as well. Otherwise, I can turn it back over to Rachel.
I just had one question. So if I understand right, you were, you're somewhat stuck with whatever the performance of the remote data source is. And so you're thinking that SCiMMA in some sense could be an aggregator of that.
That's certainly a possibility. One possibility as well is, SCiMMA could do, say, the probability region search in Alerce for you. So Alerce by itself has just a cone search built into it. But it could also say, SCiMMA could say, oh, I get everything in the 90% probability region from Alerce for that target. So this is an open question for the bigger project on kind of where we want our role to be.
Okay, you could get like a superset and then do some processing sort of locally to reduce it.
That's right.
Okay, thanks for that. Derek has his hand up.
Yeah, I was just curious, when we click that send to SCiMMA button on the spectrum, what exactly are we sending back? Just the report of an observation or
So that
anything more? Yeah, thanks. That's all.
No, it's a great question. So really, we can send back anything that SCiMMA will accept. So we've done a very simple like straw man kind of thing here, where we sent back that we got an observation of it. Now, in principle, like this is something I think we need to think about as the full project, to think about what do we want people to report. But I could imagine, say, okay, you know, we got an observation of X target, it had this classification, you know, these are the types of data we got, and even a machine readable version of the data. So you could imagine sending say a spectrum as part of that message, for example, and say this is the classification spectrum. And then a perfect world, you know, then some other TOM user could then ingest that spectrum. So when they looked at that particular target, the public spectrum would show up right when they clicked on that object as well. So that it really, we're only limited by what people are willing to send.
And we have to, that's one reason that we're looking into the machine readable things about, you might imagine sending a photometry point, but of course you want to make it machine readable so that it shows up on the other user's end. And yeah, same thing with sending a spectrum. You know, for the TNS, people often do send the classification spectrum to the transient name server. But then they don't necessarily send all subsequent spectra, but one could imagine that you could set permissions such that, you know, only people in your collaboration could send it. So then, you know, even if you were in ZTF, a closed collaboration, you could still send everything through Hopscotch, but have only the people that had the permission to see them, you know, use them. And then you could use Hopscotch as a sort of backbone for your communication within your collaboration. I don't know if we want to do that or not, but that's a possibility that we could do. So we have to think about this in the collaboration, what we want to allow and not allow, or what sort of norms we want to establish. Do we want it now because we have publish and subscribe, PubSub, we can do things like just sending, hey, I got an observation, which is not what's typically communicated right now, but it's something that's quite useful when you're right in the heat of the moment, trying to figure out which of these 20 possible candidates do I trigger my, you know, 2 hours of Gemini time that I have on. If you know that, you know, another group got a spectrum of, you know, 5 different targets, then you probably want to avoid those, even if you don't know what the results are yet. So I think we probably want to end up doing all of the above. So it's just, and you can have the observations are complete thing be sent automatically so that you don't have to click a button, because the way LCO works, we're just constantly getting data. You'd go crazy if you have to click a button every time.
Okay, cool. I think, Rachel, you have more to
Yes.
do. Yes. Okay, so we've got like 11 or 12 minutes left until the hour now.
Okay, thank you. Let me return to playing this. So I'd like to spend a few minutes to talk about a new prototype that I'm developing, which is related to the TOM toolkit, but somewhat distinct, but I think it will be of interest to SCiMMA. So broadening the focus a little from TOM systems, it's clear that many observing programs need to coordinate observations across multiple facilities. They may provide complementary instrumentation or wavelength coverage, and in the case of gravitational waves and neutrinos, different messengers as well. This obviously strongly impacts a user's observing strategy. For example, users that require simultaneous imaging from one telescope and spectra from another may choose not to observe at all, thereby conserving their limited time allocation if one of those facilities is unavailable. Alternatively, they may choose different targets, or they may observe at a different time, or they may continue to observe regardless, depending on the science goals of the team. This is particularly demanding for transient science programs where time is of the essence. It depends on having real-time status information from the observatories. And this is, although this is currently available for a few facilities, most don't provide it. However, an interesting thing happened earlier this year when the pandemic caused most of the world's observatories to halt operations due to regional restrictions, if only for some time. The developers of the Traveler Map platform organized a shared spreadsheet of information on over 140 observatories worldwide, and they enabled this updates to this spreadsheet to be crowdsourced. And this proved to be a really useful resource for observers, particularly in the transient domain. Ideally, we'd like a more scalable system for this, so I started to work on a prototype database for astronomical observatories. You can find the prototype temporarily hosted on Heroku while I'm developing it. It's designed to include all facilities, including all wavelengths and messengers, although I'm currently in the process of compiling information on them all. So for the time being, the operational server includes just LCO facilities. The main page presents a Plotly Dash interactive table of all of the facilities in the database, which also provides some handy search functions. And it holds information on all public instruments at each facility, since the availability of different instruments can differ. This page then replicates the treasure map spreadsheet functions that users can see the status of each of the facilities, plus some comments in each case. The system also provides a detailed information page on each facility and instrument with cross-links to the observatory's websites where users can get more information. And it stores information on the facility status as a function of time, and it can handle future status as well. So this has the potential to display calendar type information, as you can see in this example here, which is really useful for planning purposes. For example, for observers to plan around predicted engineering time. For programmatically accessible facilities like LCO, I'm able to update the status of this by using a cron job, which patches into the LCO system directly. But the system also provides a user interface to update the status manually as well. In addition to the online display, the system provides an API, which can be used to return a JSON dictionary of the status information. Currently, this provides output on all facilities, but you can easily imagine tuning this to be more specific, say to a date range or particular telescopes at the user's request. I'm also developing a suite of publicly accessible tools to interact with this system. At the moment, this includes some simple command line tools written in Python, and you can see here displayed an excerpt from the JSON dictionary that's returned. The status can also be updated by API, which I think will be critical in the long term to keeping the information current. Oops, sorry. The idea was that observatory operators would have a login to the system, which would allow them to update the status of their own facilities. Everything else would be public. And my reasoning is that the easier you make this to do, the more likely they are to actually include that process as part of their daily operations, or ideally make it programmatically and automatically updated. And we've considered future possibilities such as a Slack bot or some other easy to use tool to make it simple. So to wrap up with a caveat, this is very much a work in progress. I'm currently working to include as many observatories and instrumentation as possible. And I also plan to update the display tools included, but I thought it would be interesting for everyone to see this idea and in development. So with that, thank you for your attention, and I'll be happy to answer any questions.
Thanks very much, Rachel. So we have time at least for 2 or 3 questions, I think, if people want to raise their hands. I actually have some questions of my own, but I can ask those in another venue if people have questions. Okay, well, I will ask one of my questions then. I was thinking back to the TOM toolkit in particular, although this will also apply to the observatory system. And I see there are a couple of hands, so I'll just be very, very quick with my question. How, if an observatory wants to get involved in this, do you have a sort of a laid out roadmap for them that they can quickly sort of integrate, or would it be done by sort of ongoing consultation? Or
I think while it's in the prototype stage, the best bet is to contact me. I'd be happy to talk to them, and I'd like to hear from observatory operators to find out what tool would be most convenient for them I can easily set them up with an account and they can start pushing updates to the system. But it would be really interesting to get feedback from observatory operators as to what is the easiest way to integrate this with their workflow. Is it a command line tool? Is it they update their own operational systems to talk to the API? Would they prefer a Slack bot? I would be very interested to hear from people.
Great, thanks very much. So Rahul first, and then after that will be Derek. So Rahul.
Yes, I just wanted to go back to the spectrum question that was raised. And essentially what I'm trying to understand is, are you thinking that the spectrum should be reduced and you just get the reduced data with a very common API, or has there been any thinking beyond that, or what do you think is actually practical when you include observatories other than, say, a few like LCO?
So that sounds like it was referring to Curtis and David's SCiMMA demonstration. So Curtis, do you want to answer that one?
Yeah, sure. So there's several ways that I could see that working. So I think as we move forward, observatories in general want to have better and better automatic reductions that we can then include in something like this type of alert. And if the data, for example, is already agreed that it's going to go public instantly, you can imagine, say, NSF open time for, say, Gemini could then go to, it'd just be automatically public, automatically reduced, and it could go through this system back into Hopscotch and could get reported automatically. For some of the other ones, you may have a little bit of a slower process, and you may have a person like an astronomer in the loop and saying, okay, I got the data, I'm reducing it, and then once you get the reduced data, then you can click a new TOM to say, okay, now upload the reduced data. I think that's really customizable depending on the workflow that we want.
Okay, thanks. So a variety. Great.
Absolutely.
Okay, and so Derek, you have a question as well?
Yeah, I wondered if you could just repeat briefly. You had said you would appreciate some support from Hopscotch on integrating some of the broker inputs into the TOM toolkit somehow, and I just missed. I wondered if you could just repeat that for us here.
So Curtis, I think that was your section again.
Okay. Did I say that? That's no. So
yeah, something you were hoping SCiMMA would help take care of, basically. Yeah.
Right. So I mean, there's a lot of options for things that SCiMMA could do. One of the things that I had in mind is, say, converting the probability map, so those contours, and then doing those type of searches on Alerce or something like that. So they could work as an intermediary between some of the direct brokers, which their primary job is to feed alerts and all of the alerts and filter them down. This doesn't necessarily have to be in SCiMMA. This could be something that's on the broker side as well, but it is one of the options. So that's what I was thinking. That's what I had envisioned, at least in that.
So something like anticipating the obvious broker related searches that are associated with an alert and sort of pre-computing or pre-fetching those.
Yeah, basically. So I could imagine that being, SCiMMA providing some of the filters to Antares, for example, to say, okay, only get me the targets that are within 3 days and in the error region of the LIGO event or something like that. That's only one possibility. There's a lot of different possibilities we could do, but that's one of the things that I was thinking of.
Got it. Yeah, very reasonable. Thank you.